things within the Science Mission Directorate. So up next, we have Dr. Joe Westlake from our Heliophysics Division.
Thank you so much. Really appreciate it, Steve. Okay, so I want to give you guys a flavor of what we've been up to in heliophysics. I want to start with the amazing work that we did this last year in the Heliophysics Big Year. So when you think about the Heliophysics Big Year, how many of you guys saw an eclipse? Anybody see an eclipse? Yeah, okay. How many of you guys saw a total eclipse, total solar eclipse? Yeah, it was amazing. How many of you all saw an aurora this year? Saw the northern lights, the southern lights, saw some beautiful fireworks in our skies. So our Heliophysics Big Year started with the annular solar eclipse late last year, and went well into our total solar eclipse in April, in which we actually went through and really made an impact across the U.S. We were able to reach millions of people. We were able to interact with the public and really tell folks the special nature of our sun and of our heliosphere. And being able to really see and witness the solar corona with your own eyes is a magical activity. So I hope you all have the opportunity to do that at some point. Our Heliophysics Big Year wraps up this year. It wraps up at the end of this year, December 24th, when Parker Solar Probe, which is behind me, not here, but like there, over on the other side. If you haven't gone over to see the life-size Parker Solar Probe on the other side, please go do that. It has real hardware on it too, so there's some amazing stuff to see. Go ask folks and understand what went into our mission to touch the sun. I want to tell you guys a little bit of a story and walk through the strategic missions within heliophysics and tell you a little bit more about why we do what we do in heliophysics. So from its vantage point at Earth, the Solar Dynamics Observatory is constantly observing the sun. It is giving us a heads up and understanding a look at the solar atmosphere and at activity in the solar atmosphere as before it comes to us. Its vision in that wonderful multi-wavelength understanding. Let's see here. Let me get this thing to run. There it is. Okay, when we see the multiple wavelengths on the sun, you can actually look at the different layers of the solar atmosphere. Solar Dynamics Observatory allows you to really see under the solar atmosphere, under and over the photosphere in ways that you wouldn't be able to before, and in really ways that are amazing to be able to assess and understand the activity in the solar atmosphere. SDO has been up and running for since 2010, and it's a mission of discovery. It's a mission that has allowed us in many ways to observe the sun so much better and so much clearer. I'll say, even when the Science Operations Center floods, we still get data from this mission back, even if it's not served to the community. I'm so sorry. And hopefully soon we'll have the service of SDO back out to the community soon, and we'll be seeing all of the activity in solar maximum as it comes forward. You know, when you look at the sun and you see that close-up view of the solar activity, it's hard not to be amazed. It's hard not to feel like you have a connection to the star. You have this connection to the great, turbulence and solar atmosphere and all these major activities that are going on. And being able to see solar activity in such great detail is an incredible thing. I mean, have you actually sat back and looked and thought how lucky we are to be able to see the sun in this kind of detail, to be able to witness activity as it's going off, and to be able to see the magic and really understand what's happening there? So that leads us to some of our more explorational missions, some of the more technological forward missions. And this leads us to a mission that we're actually launching this year, early this year, with Punch. Punch is a 4 small satellite mission to actually go in and look and understand the inner heliosphere and look at that connection between the solar atmosphere and our Earth, watching coronal mass ejections, watching activity as it comes off of the solar atmosphere and comes up to Earth. And you can see from these 4 small satellites, so this is an innovative approach to pushing forward what would be a very large, very expensive telescope in a very creative way with the Punch mission. And the way this does this is that it maps with these three imagers plus one, the inner heliosphere. So you can actually see coronal mass ejections. You can actually see the activity as it goes out into space. Here you see the different fields of view of Punch as they rotate around and see. And you can see, for instance, here, a coronal mass ejection coming out towards the Earth. And we'll be able to see it as it progresses and not just see it, but also look at it in polarized light to actually understand the directionality and understand the flows and understand the physics behind what's happening. So let's take a minute and follow one of these coronal mass ejections as they go closer to the Earth. Let's take a minute and watch as this happens and try and tie together our field of heliophysics into one. So when we look at that, the first thing that it encounters on the way out, we see it with our eyes, but then we have Parker Solar Probe, which again is behind me. Parker Solar Probe coming into the solar atmosphere. This is our mission truly to touch the sun, and it's a mission that has gotten closer than any other to our star. It has gotten within the solar atmosphere, and that's an amazing feat of engineering and feat for our humanity. I would encourage you guys to go over and have a look at the Parker Solar Probe model, but also the shield itself. The shield itself is an engineering model of the carbon-carbon shield that was put on Parker Solar Probe and is a key example of how technology has pushed forward our capabilities in heliophysics. As that coronal mass ejection comes out towards Earth, it's going to encounter our assets at the Sun-Earth L1 point. At that Sun-Earth L1 point, we will soon have a new mission, a new strategic mission, IMAP, hanging out, ready to understand and analyze particles as they're accelerated, as they're pushed out towards the Earth. With the IMAP mission observing at L1, we won't just look at what's coming towards Earth and look at how things are pushing in that direction. Let's see here. Struggling with the playing. Anyway, so the IMAP, okay, there it is. Hey, there it is. Look at that. So this is our IMAP mission. The IMAP mission, of course, is not just looking at the particles as they come up to L1, but it is really imaging the heliosphere. So the bubble, the expanse of our sun, the effect of our sun on the local cosmos, on the local interstellar medium, IMAP measures that and will actually take an image, take a scan of what that heliosphere looks like and what the dynamics of that heliosphere are. Truly a mission of exploration in that regard. But then when we come in close to the Earth, you can see one of these coronal mass ejections impacts our magnetosphere. As it impacts our magnetosphere, that's our protective shield. That's the shield with which, life exists within the Earth. As one of those coronal mass ejections comes up, you can see it impacts the magnetic field, deflects, moves particles around, but also, we want to look at the connections onto how solar energy comes into our magnetosphere. And that's how our magnetospheric physics operates. When you see one of these coronal mass ejections, they come in and magnetic reconnection, a process that we've studied in detail, gory detail, with a magnetospheric multiscale mission. This is yet another one of our strategic missions with the magnetospheric multiscale, and it was looking at the microphysics of how magnetospheric reconnection, how energy comes from the solar wind into our magnetosphere. This mission flew, and with a coordinated multi-spacecraft view of that magnetic reconnection, really rewrote the physics and rewrote the physics books on how magnetospheric reconnection happened. And that pushes us into the next realm of clever, innovative missions. So we look at that multi-satellite, multi-spacecraft view, and the next one up is EASY. So EASY is a mission to look at the Zeeman splitting of auroral lines. Now that sounds a little wild. Zeeman splitting is actually when a magnetic field is operating when a visible light or when some light is going in. It splits the light into different parts based on how strong the magnetic field is. The technology in EASY that's been infused into this mission has allowed us to go from having multiple magnetic measurements in all sorts of different places to a set of 3 observers that allows us with these 3 small satellites to observe the 3D structure of the magnetic field in the aurora. That's an amazing achievement and an achievement that would take so many more launches if we didn't have this technology. And that leads us to the TRACERS mission. TRACERS is another one of our small explorers going up this year. And TRACERS allows us to actually see how the magnetic field of the Earth traces out into the solar wind. And understanding that connection from the solar wind, from the sun to our Earth, tells us how particles, how energy transmits its way down into our magnetosphere. So that brings us to the next set of strategic missions that we're pushing forward. GDC and dynamic are where the rubber hits the road. So as we get closer and closer into the Earth, this is where terrestrial weather meets space weather. When we see hurricanes, when we see volcanic eruptions, when we see other things, they actually propel themselves out into space and affect where our upper atmospheric measurements, where our upper atmospheric spacecraft are, where the International Space Station is. And GDC and Dynamic are there to measure that upper atmosphere and understand the composition, understand the dynamics, and understand how that upper atmosphere works. We haven't had proper measurements in that area for quite some time, and we're looking forward to doing that again with GDC and Dynamic. And then that brings us into back here at home, right? So as you think about, as we've stepped closer and closer and closer down to the Earth, we've been able to see more and more of the impact of the sun, not just in our need for sunscreen, but in how we affect and operate at the Earth, how we affect and operate in the upper atmosphere. And you can see again how we've touched humanity over and over again this year with the Heliophysics Big Year, with the folks that we've had that we've interacted with throughout the year, throughout our eclipse activities, which you can see the multitude of people looking up at the eclipse. This is pre-eclipse, leading up into that area. Really, really excited this year, and really, really happy to have really contacted so many people and had so many people witness the solar eclipse and see the corona with their own eyes. And with that, I would like to thank you all for your attention and your excitement about, there it is, about heliophysics and our heliophysics big year. I want to note that we changed this a little bit in our approach. In NASA Heliophysics, we also have the Aurora. We have other things as we push forward into the new year and into Solar Maximum. So really excited for that, and excited for all the work that you all are doing to support heliophysics. Thank you so much.